Dr. Ranjani Parthasarathi is a professor in Department of Computer Science and Engineering. Her area of specialization is in computer architecture and computer networking. She had guided more than 5 PhD students and currently guiding 5 PhD students. She had published paper in more than 50 national and international journals. She worked in many sponsored projects and she got IBM Faculty Award for 2008.
Welcome to the UGC lecture series in computer science. The broad topic that we are looking at is networks, and in today's topic we will be looking at some of the details of the physical layer. We will specifically be looking at conversion of analog data to signals. When we talk of signals, the signals could be digital data, digital signals or analog signals. So, we will look at how analog data gets converted into signals. So, we will look at analog modulation and we will also look at analog to digital conversion and encoding techniques. So, data as we know could be analog or digital, and signal again could be analog or digital. So, we are looking at a situation where the data is analog and the signal could be analog or digital. So, we are looking at how this data, analog data, is going to be converted into analog signals or into digital signals. That is what we will be looking at today, the techniques which are used for doing this transformation. So, if you look at analog data being transformed to analog signal, let us look at what actually is to be done. Any analog signal we can say is characterized by 3 parameters. So, if you take a signal like A sin 2 pi fct plus 5, you have the amplitude A, you have the frequency fc and you have the phase phi. So, one of these could be changed to represent the analog data. So, that is the idea that is used. So, you have 3 parameters, any of these 3 parameters could be used to represent the analog data. So let us look at how you are able to represent that. So, if you have a carrier signal xc of t and you have A sin 2 pi fct plus 5 as the that carrier signal, changing the amplitude A gives me the amplitude, gives me what is called as amplitude modulation, and changing frequency fc gives me what is called as frequency modulation, and changing the phase phi gives me what is called as phase modulation. So, we refer to it as AM, FM and PM. AM refers to amplitude modulation, FM refers to frequency modulation and PM refers to phase modulation. In amplitude modulation, you have a carrier signal xc of t which is represented as A sin 2 pi fct plus phi as we just saw. The data signal xs of t could be another, for instance let us assume that it is another sine signal, As sin 2 pi fs of t, As is amplitude, Fs is its frequency. Now, the modulated signal xm of t is obtained by varying the amplitude A in accordance with the data signal xs of t, that is by adding the As sin 2 pi fs of t to A, you would get something like A plus As sin 2 pi fs of t into sin 2 pi fct plus phi. So, this would be the modulated signal xm of t. So, you can see that the amplitude of this signal is changed in accordance with the data signal xs of t. Now, normally there would also be a factor, a multiplication factor, a scaling factor of say some m which would be multiplied with this in order to make sure that you get a signal which is represented reasonably without any errors. Okay. So, if you look at how the signal will look like, I think this would probably make things a little more clearer. So, let us say this is our carrier signal xc of t which is at this particular frequency fc of t, and this is the modulating sine wave signal, this is our fs of t. So, now what would happen is the amplitude of this carrier signal is changed in accordance with this modulating sine wave signal. So, what you have is something like this. So, you have the amplitude of the signal of the carrier signal changed in accordance with the modulating sine. So, if you look at the envelope of this signal, you will find that it is pretty much the same as the modulating sine wave signal. So, what we have achieved is that you have changed the amplitude of this carrier signal in accordance with the modulating sine wave signal, and this signal is what is transmitted to reach the other side. And from the other side, you have to recover this modulating sine signal, which can be done very easily by understanding that it basically is the envelope of this particular signal. So, this is what is done in amplitude modulation. It is a very simple technique. Next, we will look at frequency modulation. In frequency modulation, again we will take the same example of having a carrier signal xc of t which is A sin 2 pi fct plus phi and data signal xs of t which is As sin 2 pi fst. Here this frequency fc is going to be modified in accordance with the data xs of t, that is you will have your modulated signal xm of t where A sin 2 pi fc plus as sin 2 pi fs of t to t plus phi. That is, what we have done is this fc of t is being changed in accordance with as sin 2 pi fs of t. So, this would be the modulated signal. Okay. So, this signal if you look at how it gets actually represented, you will see that it looks something like this. So, you have this is our carrier signal with a frequency fc of t. Now, this frequency is what is going to be changed in accordance with the modulating sine wave signal. So, this is our modulating sine wave signal. So, you can see that as the value changes over here, there is a change in the frequency of the modulated wave, and you can see that it decreases and then it increases in accordance with the modulating sine wave signal. So, now this is our final FM modulated, that is the frequency modulated wave or the FM wave. Now, this FM signal is what is transmitted to the other side, and on the other side you will find that by tracking this change in frequency you can recover the original signal. So, that is you have to track the change that has occurred in the frequency. That is what is done in frequency modulation. The third type of modulation that is used is phase modulation. Now, in phase modulation what is done is, again taking the same example, the phase phi of the carrier signal is modified in accordance with the data. So, you will find that you have a sin 2 pi fct plus phi plus as sin 2 pi fs of t. Now, you can see that both phase modulation and frequency modulation have almost similar properties. That is, in the sense that it is the component which is there within the sine which gets modified. So, in fact, phase modulation and frequency modulation together are also referred to as angle modulation. So, anyway, first let us look at what the phase modulated signal looks like. So, if this is our carrier signal again and this is our modulating sine wave signal, phase modulated wave looks like this. That is, the phase of the signal changes in accordance to the modulating sine wave signal. If you look at the picture, a frequency modulated wave and a phase modulated wave will almost look similar. That is because it is the frequency component, the frequency plus the phase component which is there, which is within the sine component which is changing. So, here again phase modulation, in phase modulation this phase modulated signal is what will be sent to the receiver side, and on the receiver side by tracking the change in the frequency you will recover the original signal. So, these are the three modulation techniques available for amplitude, frequency and phase modulation, which is available for analog data being transmitted as analog signals. Now, so let us just look at a quick comparison between these three, AM versus FM versus PM, that is amplitude modulation versus frequency modulation versus phase modulation. Frequency modulation and phase modulation can actually be treated together, as I said, because they can together be represented as angle modulation, because it is the angle that is modulated. So, if you look at AM amplitude modulation is very simple to implement, but it is subject to noise. Now, why do we say it is subject to noise? That is because you can see that in amplitude modulation it is the amplitude which changes. So, when the amplitude changes, if there is any noise, that noise will again get added to this amplitude, and so you will not be able to detect whether it was a noise, whether it was actually a change in the signal value. So, it is difficult to remove the noise from the amplitude modulated signal. So, that is one reason why the amplitude modulation signal is not preferred for very high quality signal transmission. But if you look at FM and PM, both frequency modulation and phase modulation, both frequency modulation and phase modulation have better noise immunity. The reason is that the amplitude is constant. So, because we could probably just go back and take a look at the picture that we have here. So, you can see that in this case in phase modulation the amplitude of the signal remains constant. So, if there is any noise that gets added over this, it can easily be just chopped off. The same thing is true for frequency modulation as well. So, you can chop off the noise and recover the original signal, and what we are looking at is not change in amplitude, but you are looking only for change in frequency and phase. So, in that sense it becomes easier to detect the signal even in the presence of noise. So, that is one reason why frequency modulation and phase modulation give better quality, and this is something that all of us have experienced, that we keep experiencing whenever we listen to an FM transmission over an AM transmission. An FM definitely gives us a better quality. So, that is the advantage that we have with FM and PM. Anyway, coming back to digital signals, analog data being represented as digital signals, because we are more and more moving towards digital communication, we need to know how analog data also get transmitted as digital signals. So, what do we need to do in order to transmit data, analog data as digital signals? Analog data is first converted to digital data, that is the first step. The second step is the digital data then can be transmitted as digital signals using any encoding scheme. Now, in a previous session we have already looked at how digital data can be transmitted as digital signals using encoding schemes. So, once you have converted your analog data into digital data, it can be transmitted using any of the encoding schemes which are available for transmitting digital data. And how do we do this conversion? That is the crucial part. Thus, how do we convert the analog data into digital data? So, this is done by means of what we call as sampling. That is, you sample the analog signals and note the discrete amplitudes at specific intervals of time. That is, you take an analog signal and you sample it at various points of time and you note down what the amplitudes are, and those amplitudes are the ones that now have to be sent as digital data. So, let us look at how that is. This is a simple example of some signal that you have here. Now, this signal is being sampled at some discrete intervals of time, and we note down what the values are. So, for instance, for at this particular sample the value is 0.92, and at this particular sample the value is some 1.52 and so on. So, you just note down these sample values, and these sample values are the ones that have to be now converted as digital data and sent as digital signals. So, the first question that comes here is, how often should I sample this? That is, what should be the sampling frequency? Why am I concerned with the sampling frequency? It is very easy to understand it by just looking at a signal like this. So, let us say for instance I sample at very large intervals of time. That is, I take a sample here and then I take sample over here. Now, what will happen in that case? There is a change that took place from here to here which I would have missed. The change that happened from here to here is something that I would have missed, and when I look at the data that I have, the data will show that the previous sample was 0.9, the next sample was 1.1, and the fact that the signal actually went to 1.5 and then came to 1.1 would have been completely missed. So, you need to make sure that you sample quite frequently. But if you sample very frequently, then what happens is that you have many samples that you generate, and then you need to have so many more samples of data that need to be sent. So, we always try to arrive at a ideal sampling frequency. So, how do we arrive at this ideal sampling frequency? So, now that is given by what is called as the Nyquist sampling theorem. Nyquist came up with this very important result that the analog signal has to be sampled at a frequency which is greater than or equal to twice the maximum frequency of the signal, in order that you can recover all the information that is present in the signal. Let me just explain this. If a signal has a frequency spectrum ranging from some f min to f max, say from 0 to 500 hertz, so 0 would be my f min and 500 would be my f max. If a signal has a frequency spectrum which is ranging from f min to f max, then the sampling frequency fs must be greater than or equal to twice f max. So, if I took this example of 500 hertz, twice f max would be 1000 hertz. So, my sampling frequency should be greater than or equal to 1000 hertz. This is a very important theorem that was proposed by Nyquist, and he has proved that this sampling frequency fs being greater than or equal to twice f max is sufficient to recover all the components which are present in the signal. So, let us take some examples of how this Nyquist sampling theorem is used. Let us look at an example of sampling frequency for human voice. Now, frequency spectrum of the human voice typically ranges between 300 to 4000 hertz, 3300 hertz. So, let us just approximate that to 300 to 4000 hertz. So, now the f min here is 300, f max is 4000, therefore, twice the maximum frequency would be 8000 hertz or 8 kilohertz. So, my sampling frequency must be greater than or equal to 8 kilohertz. Now, naturally, if 8000 hertz is enough, any value greater than 8000 hertz is also sufficient. So, we can say that 8000 hertz is sufficient for sampling human voice. So, 8000 hertz or 8 kilohertz is the sampling frequency that is normally used for human voice. So, let us say I have another signal which has a bandwidth of 5 kilohertz to 9 kilohertz. So, 5 kilohertz to 9 kilohertz, that gives me 9 kilohertz is my maximum frequency. Therefore, the sampling frequency for this should be twice the maximum frequency or twice 9 kilohertz, so it should be 18 kilohertz. So, that is how we arrive at the sampling frequency. So, once you arrive at the sampling frequency, the job is very simple. You just need to sample and then you need to represent these samples using digital data. We will take a break and come back and look at how the samples need to be represented. Welcome back after the break. So, we were just talking about how analog data is sampled and these samples are represented using digital data. So, we just need to look at how these samples have to be represented. For doing this representation, we use a process called quantization. So, let us look at what this means. This quantization process is the process of representing the sample values using different quantization values. For instance, let's just take an example of what we do in pulse code modulation or PCM. Here n bits are used to represent each sample. Now, these n bits, using n bits you have some value and the sampled value is approximated to the nearest n bit value. So, let us look at how that is done. So, for instance, if I take 3 bits I would get 8 different values and I could represent the sample using one of these 8 values. If I use 4 bits I would get 16 values and I would represent using one of these 16 values, and if I use 8 bits I would get 256 values, 2 power 8 is 256. So, I could represent my sample using one of these 256 values. Now, it is very easy to see that if you use more number of bits for representing, you will get a better representation of the sample signal. If you use fewer bits, then the approximation is very coarse and therefore, there would be more error that may occur when you do this representation. This is something that we need to guard about when we talk about quantization. So, let us look at how this is actually done. You can see that in this example we have used 3 bits to represent each pulse amplitude, and if this is my analog signal that I have, assume that each of these boxes represents a sample that I have, that is at the middle of the box I have sampled the signal. So, when I sample at the middle of the box I find that there is a particular value that I have and it is that value which is used to represent this particular signal. So, if you see this signal, this analog signal, when it is sampled over here the value let us say corresponds to 8 and let me assume that I have values starting from 0 to 8 over here, okay, 0 or rather 1 to 8. So, 0, 1, 2, 3, 4, 5, 6, 7 and 8. So, this value that I have here 8 pulse amplitudes. So, when I start over here let us say I get a value of 8, here when I sample I get a value of 7, the next sample I take is over here. So, when I take the sample over here the value that I get is 4, the next sample I take is here and here the value corresponds to 2 and so on. Okay. So, you can see that when I do the sampling, so whatever sample I have taken here until I come to the next sample block I maintain the same value. So, over here I maintain the same value, over here now I come to the next value maintain the same thing, here again maintain the same value until I come to the next block. So, the next block is here which the value is here. So, you can see that the digital samples, the digital signal that I get is it has discrete amplitudes over here. So, it maintains a value of 8, then maintains a value of 7, then drops down, maintains a value of 4, drops down, maintains a value of 2, maintains a value of 1, then goes up to 2, goes up to 5, then goes up to 7, then goes up to 8 and so on. So, this is my original wave and this would be my sampled or discretized wave that I get after doing the sampling. Okay. And you can see that there is some error in the representation which is what we refer to as the quantization noise or the quantization error. Now, what is the error? You can see that actual value is somewhere around 7.5 or something like that, whereas you represent it as 7. So, this is one of the problems that you may run into when you do this quantization. Okay. So, again this is another the same example where we have shown that the values that you got, the 8, 7 etc. are now coded as the digital values. So, I have just coded the value 7 as 111, 010 would represent 2, then 101 would represent 5 and so on. So, just showing the codes that are used at each of these sample values. So, after doing this process of quantization what you would get is a list of these digital or binary values that you have. So, 111 followed by here for instance it would have been 010, 0 or 100, then 010, then you will have 001 and then you will have 010, 101. So, this will be the list of data or the digital data now that needs to be sent. So, after doing the process of quantization you would have arrived at the digital data that needs to be now sent as digital signals. Okay. So, a little bit more of details on what this pulse code modulation and the waveforms will correspond to. So, if you take for instance an example where we have 4 different bits that we are using to represent the values. So, you will have values going from 0000 to 1111. So, that is it could represent values going from 0 to 15. So, if I have value of 000, the corresponding PCM waveform would be something like this, whereas all values are all zeros. 0001 would correspond to a single pulse 1 which occurs and in the 4th bit. So, there will be 4 bits that are represented and each bit would represent a value of 1 or a 0 depending on what the binary equivalent is. So, this is how the PCM waveform would be constructed. So, you can see that this PCM waveform is nothing but a digital waveform, and this digital data now can be sent as digital signal. Now, as I said, there can be problems with this quantization. So, what are the problems that occur with quantization and how do we deal with them? The quantization noise occurs whenever we do an approximation. So, the approximation means that it is impossible to recover the original data exactly. So, which is why we refer to this as noise, because we know that whenever there is some noise that occurs, there will always be some loss of data that is likely, and therefore, we need to have techniques wherein we are able to recover the data even in the presence of noise. So, what do we do in order to reduce this quantization noise? One of the things that we do, which is very obvious, is that you can increase the number of bits that you use to represent each sample. If you do this, then you will decrease the quantization noise. You can see that if I use, as I said, 4 bits per sample, it will give me 16 different levels. So, if I go back to this figure and see that instead of using 8 levels, if I had used 16 different levels, so I would be able to get better approximation of the original values. So, this error that I have here would be reduced. So, this is what we try to do by increasing the number of bits that you do per sample. So, if I use 4 bits per sample, it will give me 16 levels. And if I use 8 bits per sample, it will give me 256 levels. And it has been found that with about 8 bits per sample, you get quality which is almost comparable to analog transmission. So, if you are looking specifically at voice, for instance, voice transmission, 8 bits per sample, which will give me about 256 levels, will give me a quality which is comparable to analog transmission. So, with 8 bits per sample, you kind of reduce the quantization noise and get transmission quality which is pretty good. Now, let us look at how do we arrive at the data rate for this signal. What do you mean by data rate over here? There is a number of bits that have to be generated when you do this sampling and then quantization. So, now you can see that it is very easy to understand how the data rate has to be calculated. So, it depends on the number of bits per sample and the sampling frequency. If I take for instance digitizing voice signals again, my voice bandwidth is, as I said, 300 to 4000 hertz, and we arrived at a sampling frequency of 8 kilohertz going by the Nyquist sampling theorem. Now, that is you will have 8000 samples taken per second. Now, if I use 8 bits to represent each sample, you will get a data rate of 64 kilobits per second. That is, the data rate for a signal is just the product of the sampling frequency and the number of bits that are used to represent a sample. So, now the reason why we need to worry about the data rate of a signal is that when you increase the number of bits per sample in order to decrease the quantization noise, you will find that you are actually increasing the data rate for the signal. That is, if I use, instead of 8 bits, if I use 16 bits to represent each sample, I would get a data rate which is 64 kilobit per second into 8 bits, 64 kilobits per second into 16 bits per sample. So, that would be my data rate, which is double the data rate that I have over here. So, this is a problem that we have when you start increasing the number of bits per sample. So, when I increase the data rate, obviously I need a higher bandwidth for data transmission. So, we want to always keep the data rate small, at the same time make sure that the quantization noise is less. So, you arrive at a value which gives you reasonable quality. Okay. So, that is a trade off that is involved over there that we must be aware of, and it has been found by experimentation that 8 bits per sample for digital voice, for digitizing voice, gives us pretty good quality. Now, in order to reduce this data rate and the quantization noise, there are some other techniques also which are used. So, let us look at what those techniques are. One is to use non-linear quantization levels. So, what we mean by non-linear quantization levels? The quantization levels need not be evenly spaced. Now, in the example that we saw now, we saw that all the quantization levels, that if you had a total maximum value that you had to represent, it was from minimum to maximum was divided into equal number of levels. So, instead of having the quantization levels being equally or evenly spaced, you can make sure that we use a non-linear quantization mechanism, and that can help to reduce the overall signal distortion. We will just look at how that is done. A second technique that is used is that we use something called delta modulation. In delta modulation, the analog input is approximated by a staircase function, and what we do is we use only 1 bit per sample, and you just move up or down by 1 level, which is the delta level, at each sample interval. So, we will just take a look at how these two are done. I will first look at non-linear quantization levels. So, take this picture over here. I have got two signals here. This is one signal which has a lot of variation. There is another weak signal here which does not have too much of variation. Now, if I use quantization levels which are equal, okay, you will find that in this weak signal where there is not much variation, the variation cannot be captured at all, because you will find that when I quantize it, when I sample it and I quantize it, the variation is so small that all the samples will be approximated to the same value. So, I will find that the variation that I actually have in the signal are not captured at all correctly, that is because of the quantization levels that I am using. Instead, if I use non-linear quantization, what do you mean by non-linear quantization? If you see over here in the right side of the picture, I am using a value of 0 here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can see that between 4 and 10 here, I have a final level at which I am doing the quantization. That is here in the on the left side, it is they are all of equal levels. Okay, so I have 5 here, 6 here, 7 here, 8 here and 9 here, whereas here you will see that between 5 and 10 you have final levels of quantization. So, when I do this, what happens is that even when I have a weak signal, because I have final levels of quantization at these levels, I will be able to represent it better and the quantization noise that I get will be reduced. So, this is one of the advantages of doing non-linear quantization. So, this is a technique which is used in many communication systems when you take analog data and convert it to digital data. That is, we use non-linear quantization levels in order to make sure that the quantization noise is reduced. The second thing we have is delta modulation that I talked about. This is a very simple technique again. So, what is done in delta modulation is, if you look at this picture, you can understand what is happening. So, this is my analog input. Now, we start with let us say we start with some value of 0 over here, and whenever you find there is a change in the signal, that is when you find that you sample it and you find that the sample value is greater than the previous sample, you represent it as a 1. When you find the sample value is less than the previous sample, then you represent it as a 0. So, if I take this particular signal, analog signal now, and I sample it at these values, these boxes represent the places where we are sampling them. So, if you sample it over here, you will find that the delta modulation's output will be like this. You find that from here it is going from the previous value was 0, was a low value, next sample is at a higher value. So, now the delta modulation output is 1. Again the next value is also higher than the previous sample, so again the value continues to be 1. Again the next value is higher, so again the value continues to be 1. The same thing continues until we come to this part where you find that the signal is increasing, and after this point the signal starts decreasing. So, when the signal starts decreasing out here, you can see that the value now becomes 0. So, again the next value is again lower than the previous value, so the output continues to be 0. The same thing continues until this point, that is until this point. Now, here again there is a variation here, because you find that when you sample it at one point you find that it is lower, at another point you find it is higher. So, you get some values of 0, 1, 0, 1 depending on that, and then finally you have the again when you find that it is increasing further, again you have a series of 1s. So, if I reconstruct this from this is my output that I have. So, this will be my digital data that needs to be sent. So, when this digital data is now sent out, I have to now reconstruct my original signal from this digital data that I have. So, what I do is whenever I see a 1, all I need to do is I need to increase the step value. Again there is a 1 value, so this is my step value increases to 1. So, again another 1, so it increases. So, this 1, 1, 1 here, the different steps that you get will be the signal that you will get when you reconstruct the digital data that is sent. So, you can see that if you compare the analog input and this reconstructed digital signal that you have over here, this you can see has something like it looks like a staircase, right. So, it is called as a staircase function. So, the staircase function is the output that you will get, and the difference that you have between the analog input and the staircase function is referred to as the quantization noise, or the is also referred to as the slope overload noise. And when you do the quantization, again there are some errors that you have here, because you find that the 0 and 1, there is an alternating 0 and 1 which gives you some variation in the signal, which again is represented as the quantization noise over here. So, one of the advantages of this delta modulation is its simplicity. It is very easy to do a delta modulated signal, but of course, and another major advantage is that the data rate that you use for delta modulation is also low. So, for these two advantages, delta modulation is used in many places. So, as I said, it is very easy to do delta modulation. All you need to do is take the samples, compare it using a comparator and see whether the value was higher or lower. If it was higher, you use a value of 1, if it was lower, you use a value of 0. And reconstruction again is a very simple process. All you need to do again is take the binary input, keep on after a delay of 1 unit, add or subtract depending on whether the value is 1 or 0, and you get the reconstructed waveform. To summarize, what we have looked at in today's lecture is how analog data is converted to analog signals and digital signals. For analog data to analog signals, there are three techniques that we saw. One is AM, FM and PM, analog modulation, frequency modulation and phase modulation. And from analog data to digital signals, we looked at how the analog to digital conversion takes place using sampling and quantization. We also looked at how the sampling theorem is a very useful theorem, and we looked at two techniques, the pulse code modulation and the delta modulation techniques which are used. A few questions that you can try out to understand what has been done over here. Question number 1, what is the idea behind AM and FM? Question number 2, what is the major advantage of FM? Question number 3, how can analog data be transmitted using digital signals? Question number 4, what does the sampling theorem tell us? Question number 5, what is meant by quantization? 6, what is quantization noise? 7, how do we arrive at a data rate of 64 kilobit per second for digitized voice? Question number 8, what is delta modulation? Thank you.